Give me a wait for 1 more minute. Yeah. Hope I'm audible. And that I'm good in the department of and the TA for this and the being hosted on NPTEL by Professor Mehta. Already covered till 6 weeks of the course. Today in this problem solving session, cover week 7 and also some part of week 6 which was pending from uh, earlier. So we'll also cover that. Week 6 is already done. Now we'll cover week 7 and some part of week 8 because last time some part of week 7 was not finished. So we'll cover both 7 on 8 today. Okay. Also, I have seen in the discussion forum that some of you have pointed out that some of your answers were close to the range which was given in the answer sheet, but was slightly off. So I think the NPTEL staff will take a decision on that. How to. So let us start with the realization of some part of week 7, which was still left last time, and then some questions from previous year's assignments which are pertaining to that one. So we were somewhere here, we were doing the constitutive equation. So my apologies for the bad, I don't know you can see clearly or not. Solution is not good. So this is due to certain issue when the note making. From next time onwards, I'll be careful about it. For now, let us deal with it. Okay, let's again look at constitutive equations. Constitutive equations are some relations that have been developed to um, be able to have a quantitative relationship between stresses, strain rate, and temperature. Basically, to be able to describe the deformation phenomena and make prediction to how the stresses will change, how the strains will change as you roll at a particular strain rate and temperature. So there have been multiple attempts to form constitutive equations which can explain the deformation behavior of the material. Different people have brought forward different equations. So one of them is this one involving the ZX parameter. Then we have delta X, and this is a relation between the strain rate, uh, between the value of strain rate utilized and the value of stress we get for a particular value of strain. So strain rate dependence of the flow stress we can call it. Not necessarily the flow stress, but the stress at which we get that particular strain. Then you have the Sellers and Taggart relation. Relates change it and stresses, but also takes into account temperature. So this is a slightly different form of different way of a different equation to calculate the same quantity. Then we have Johnson's equation. In which yes, stresses change, strain rate, and temperature. Together. These were equations were made with certain considering um, these were made after looking at multiple experimental results and seeing the trends of strain rate with specific strain rate, specific temperature, and then trying to combine the effects of all of them together in one system. So now coming to how are the assessment of uh, deformation progression different in FCC and BC. FCC has been observed to be more uh, he has been observed to have resistance which is more temperature sensitive and its work hardening uh, region is less temperature intensive. On the other hand, BCC shows more resistance temperature sorry resistant it shows less resistant temperature sensitivity, but the work hardening temperature is more temperature. This is because of how the mechanism of work hardening and yielding in FCC and PCC are different, and that is why they are increased temperature.
So, as we saw in the previous constitutive relations, you have strain rate and temperature as independent parameters or quantities which can affect your stresses and strain. And it has been like it is understood that if you increase strain rate, then it will lead to lead to an increase in strength, while a decrease in temperature will also lead to an increase in strength. So both have a similar effect, though it is inverse, but both will lead to change in stress. So one can compensate for the other. So as you can see here, the impact strength will increase if temperature increases, while the also a continuation to this will be that the UTS at slow strain rates uh, will increase if the temperature decreases. Ah. So at high temperatures, UTS at slow is decreasing, but UTS of impact is increasing. But I think here the effect of this fraction, like increase in the in this fraction, is more because your UTS at slow strain rates will considerably reduce as the temperature increases. So this fraction increases. Impact one also will have some effect, but that I think so will be lesser because in impact thermal activation is in general less, even if temperature is high. So then looking slightly at polymers, most of our discussion is in metal, but let's look at polymers. So you can have thermoplastic or thermosetting, both have different properties. Thermoplastic will have with temperature the plasticity properties increase considerably. For thermosetting, uh, the it is more it will show good strength even at higher temperature. That is because of the different arrangement of the bond of the chain links in both of these structures. So they have a different internal structure, and due to it the mechanism of strengthening and mechanism of deformation is also different in both. I think in thermoplastic you have just weak links between bonds, um, and there's a easily the bond structure is open, so it can easily rearrange when you are trying to deform it. But in thermosetting, it is more rigid, so bonds are much more rigidly arranged, so you cannot easily shift them around just by deforming a little. You can have brittle and plastic polymers based on this. And necking occurs in polymers by aligning on and stretching of strain. So initially they will align, and that will lead to a very low modulus. But after they have aligned, then you will have stretching, which will be seen as an increase in modulus in the curve. Then decrease in temperature and increase in strain rate, similar to how it is in metals, will lead to an increase in modulus, increase in UTS, and decrease in elongation. You can think more on this on why this is happening. Then there are multiple tests which are important when it comes to mechanical testing of materials. Let's quickly go through. Torsion test, so basically rotation of a body with a fixed end, and this leads to a biaxial stress state. So yeah, this leads to a biaxial stress state. You can uh, in search diagram you can see how it is biaxial. I won't show here, but that is important to understand. So you can have a very high. So the implication of that is that you can have a very high maximum shear stress with respect to the mean nominal stress. Mm, So maximum shear stress can be considerably high when compared to other mechanical tests. That's why torsion test can um, give you the effect of shear stresses on your material's deformation behavior. Then we have compression test. Here, friction plays a major role while the compression is happening, and it affects the properties you measure. Hmm. And due to this friction at the surfaces at top and bottom, you have some non-uniformity. Uh, so even over the cross section of the specimen, you will have non-uniformity of pressure. It's called a friction hill. So these can complicate the analysis of the test results because they are causing non-uniformity in the deformation behavior. We can have 3-point bend test, which has a specific geometry and tells you the flexural strength. How how does your material respond to bending? How easy it is to bend it? Then we can also look at glasses. Glasses also have a completely different structure. At high temperatures, they will be mm, amorphous. So above Tg they'll be amorphous, but below that they will start to crystallize, and they have a specific Tg glass temperature and melting temperature. They also show time dependent deformation because of their amorphous nature, and so they are kind of viscous materials. Even at lower temperatures they will deform, show some time dependent deformation, which is much more pronounced than in metals or crystalline materials. And this is because of their glassy structure. There is a sudden change in properties at as your temperature goes beyond Tg plus or minus, and that is because it's basically a phase, drastic phase change that is happening. And at temperatures more than Tg, the sensitivity of of uh, deformation to strain rate is very high. Uh, Strain rate sensitivity of the strength for the sensitivity of strength, the strain rate is very high. Next, let's look at some mechanisms of deformation. One important one is the thermal activated deformation. So, thermal activated deformation is uh, relevant for short range obstacles where your thermal fluctuation local can lead to local displacement of your atoms, which can help in surmounting obstacles, maybe help dislocations to move uh, away from obstacles and continue gliding, for example in dislocation climb. But it can also lead to other kinds of uh, thermal activation can help in other mechanisms also, such as mm, atomic diffusion, leading to some training, or mm, for dislocations to move beyond any obstacles, or even anything involving diffusion in general, grain boundary worsening. For all of these things, thermal activation has a contribution. And you can quantify it by this formula: gamma dot strain rate equal to rho b into del into v into e raised to minus delta g by kt. So you'll always have this minus delta g by kt thing because it is a this is basically what we call as Arrhenius equation. So this is basically because of the stochastic process, the stochastic nature of diffusion. So due to that, you have to use this Arrhenius equation whenever diffusion is involved. So, and here we have something called V star. So I'm not going into details, which is average volume or activation volume of the dislocation structure involved. And so by this formula, you can relate the um, thermal activation to the strain rate observed. Mhm. And that way you are relating strain rate and the temperature. Then one more kind of testing is impact testing, common for application from an application point of view, where you this is also impact test, but here you are trying to see what is the fracture toughness of your material, and how it is dependent on the temperature of impact, temperature at which impact occurred. So at high temperature, the plasticity is more and it will show more of ductile failure. It will be able to absorb more energy, but at lower temperatures, it will show brittle failure. There will be very quick crack propagation, plasticity will be less. So whether it will be brittle or ductile will depend on majorly three factors: temperature, strain rate, and the stress state, whether it is triaxial or plane stress. So what is the stress state of that material? Plane stress usually gives higher plasticity, like plasticity will be more in plane stress than in plane strain or in triaxiality. Mhm. So depending on what is the yield strength, you can have, if it is very low, you can have plastic deformation, but if it is higher than the fracture strength, then you will directly have fracture first. And you can quantify this temperature dependence by this number called DBTT, ductile to brittle transition temperature. There are different ways of defining DBTT related some parameters such as FTP, FATT, and DT. Hmm. Depending on so NDT is nil ductility temperature, no ductility to some ductility. FTP is I think full ductility to some brittleness, that way. And composition and microstructure of your material will be what will be affecting the DBTT, because it is in a way characteristics of the material. So depending on the microstructure and composition, that will change. Okay. So creep, I think we can go to later, a bit sometime later, like after, because we have some assignment questions of week 7 which we did not solve. So let's go to that. Then we'll go to week 8 content and then it's assignment questions. Okay. I know I had shifted the class, so maybe because of that, you people could not join. This was uh, make a change in schedule at short notice. But I'll suggest you can watch the lectures if you have any doubts. Go to the discussion forum and post if there's any specific you want to uh, get answered. So let's look at assignments. Mhm. 8, 9, and 10 have not been solved. I hope it is visible. Hmm. Okay, so let's solve question 8. A high strength material such as titanium alloy has a low notch toughness and fails by low energy rupture at high temperature. Statement 1. So yes, it will have a low notch toughness if it is a high strength material, because that is the effect of the microstructure. So generally strength and toughness do not go together, because those factors which lead to strengthening also can lead to reduction in toughness. It's not always. In certain situations you can have both. You can cleverly design a material such that you have both. But this is true, and it fails by low energy rupture. So it the failure can be either by low energy rupture or by um, it can be either low energy rupture or just crack propagation starting from the crack initiation at some high energy side and just immediate propagation either through the boundaries or through the grains. And of course, we have a notch here, so directly crack can propagate from there. But at high temperatures, I don't think we will expect to have a very low toughness, because it becomes a ductile material at high temperature. So I think this might be false. Temperature can have a very high effect on your notch toughness. So at high temperature, you should have a good toughness. So second statement, all HCP and BCC metals have a ductile to brittle transition temperature. Uh, I think most should have a brittle to ductile transition temperature, but certain materials are brittle even at high temperature, for example in HCP, because they do not possess enough number of slip systems to accommodate the um, grain bound accommodate strains at the grain boundary. So basically, you need some at least five slip system independent slip systems for being able to accommodate strains such that you have grain boundary compatibility being maintained. So because the grain shape is changing, you need to make sure that the at the boundary you do not have any void formation. And this you can do by having stresses, having slip systems which can allow for plastic deformation and change the shape of grain such that your boundary compatibility is maintained between two grains. But in some HCP ones, it might not occur. So this is false. Statement 3, dispersion strengthening hinders grain growth and improves impact resistance of ferritic steel. Dispersion strengthening can hinder grain growth, that is true. But whether it will improve the impact resistance of ferritic steel, I think it will, at least due to the finer grains it will, because these finer grains can act as boundaries to the initial crack propagation. So this is true. The cracks will encounter more of these grain boundaries. Statement 4, in case of typical friction hill, when enterprise friction factor is equal to 1, there is no relative motion between the workpiece and tool. This should be true because you want more friction when compression is going on. Sorry, you want less friction. Yeah, so when compression is going on, you want less friction so that the surface can slide very easily and expand in such a way that the overall deformation will be uniform. There will not be any bulging occurring in the middle. So you want the friction to be low, but if it is equal to 1, that means it's very high. So there will be no relative motion between the workpiece and the tool. There will be direct bulging even for smaller strain. Your material will bulge out. So this is true, undesired, but it will happen if your friction is high. So the correct answer is FTT. So FTT may be this one, but first one we had some confusion. where we have titanium alloy, low notch toughness, and fails by low energy rupture at high temperature. This is a very ambiguous statement because you don't tell what is the high temperature. But in general, if they have told a high strength material, that means that it will have a lower toughness, lower DBTT, sorry, higher DBTT compared to uh, medium strength material or medium strength alloy. And due to the high DBTT, we expect that even at high temperature, it might be brittle and fail by low notch toughness, uh, fail by low energy rupture and have low notch toughness. So this can be true. We can just understand it that way. But this is assuming that we are even at highest temperature, the DBTT is not reached. I think now we will be correct. True, false, true, true. Let's go to the next one. The nil decree temperature is the temperature at which nil ductility temperature is the temperature above which you will have some ductility, but below that it will be completely fracture. So fracture takes place with no prior plastic deformation. So with no prior plastic deformation. When the plastic deformation just starts, we say that that will be the NDT, nil ductility temperature. During a compression test, what is responsible for the concavity of the flow gas? Concavity of the flow gas. So let's see how the flow curve will be. So if it is like this, then yeah, many times I think it's like this only. So many times you can have this concavity where it changes its what we call as the curvature. That I think is due to barreling because it becomes easier for it instead of having longitudinal strain, it is just having transverse strain in particular cross sections only, not overall throughout the sample. So that is easier than uniform straining, I think, this kind of barreling. So what happens is in the middle you have very high stresses, while in the on the sides you have lower stress. This is the friction hill, right? And this leads to this kind of barreling and reduction in the flow stress, which is kind of not normal, difficult to work with. So with this we finish. We didn't see the answer, no? Mm-hmm. Yeah, that was assignment 7 of 2023. Now let's move to creep, week 8. We'll have the whole of week at 8 on creep only, so we'll see it in somewhat detail. In creep, so firstly, what is creep? Creep is the time dependent deformation of any material, usually at either constant stress or constant load. This is constant true stress or constant, no, constant engineering stress, which is the constant, constant stress here means constant true stress, and constant load means constant engineering stress, because you only look at the initial cross section and use that for your stress computation. So both of them will are called creep, and both have certain relationship. So here also we have this kind of equation which resembles a constitutive equation, and we are trying to do this only, relate the properties of the material, the testing conditions, and here we have creep we are looking at. So the creep rate, the stress that was applied, which led to creeping, and the time for which the creep the creeping happened or deformation happened. So slowly we'll look at the response of materials, the stress strain response of materials, and then come up with some mechanisms to explain what might be causing that, and also experimentally validate it by looking at by looking at how the microstructure changes for those conditions of creep. So this is actually body of work which has been going on since at least last 70, 80, 90 years. People have been trying to investigate uh, time dependent deformation, come up with models which will fit their results, look at the post deformation microstructures, and then build phenomenological models based on those microstructures, trying to explain the results they are getting. So by doing all these study, they have come up with certain equations to model creep in certain conditions and in certain materials. Yeah. So we have three stages of creep. The initial state, which is called stage one, or also stage one, where we have um, instantaneous strain followed by some transient. So as written here, instantaneous strain. Okay, in this it is not opening. Yeah, you have instantaneous strain. You have the transient, which is called stage one. Then we can have a steady state. And after steady state, we can have something called tertiary creep, which is a accelerated creep, and it's difficult to study as well as not so relevant because it is much more shorter. And this is where the fracture process begins. So fracture starts to happen, flaws get created, and they quickly lead to failure. So you have the instantaneous strain, transient, steady state, and tertiary. we have something, and here temperature plays an important role because this is time dependent. So majorly what this time dependent signifies is that you have enough time for thermal processes to play play a significant role. So diffusion plays a big role in almost in or not almost in all creep processes. Diffusion plays a big role, and you quantify it by what I had earlier also mentioned, the Arrhenius Arrhenius type of equation, d naught e raised to minus qs by kt. So here qs is for substitutional, sorry, self diffusion. So same kind of atom diffuses in its matrix. It's also called vacancy mobility, related to vacancy mobility, but self diffusion based. And this is the equation for that. It will come up in all the creep equations we'll look at later. Also, we have something called equicohesive temperature, the temperature at which both grains and grain boundaries have the same strength. Above that, grain boundaries will be weaker, while below it, grain boundaries will be stronger. And we also have something called critical temperature called 0.5 Tm. And this is the temperature where usually creep deformation uh, starts playing a dominant role in so creep starts playing a dominant role in deformation. Below it, you can have other processes also, gliding, dislocation, gliding, or stress, more of time independent or quasi-static processes dominating. And this 0.5 Tm is due to a certain characteristics of the activation energy. So, Sir has explained that. And here you have Qs equal to 38 Tm, the activation energy. This pen is not good. Okay. Qs equal to 38 atm for self diffusion. 38 tm. Mm. So the reason for different stages is because the internal mechanisms change over time. So in stage one it will be different, stage two it will be different, three it's different. So in there will be change in microstructural features as the creep progression takes place and deformation progression takes place. And for steady state creep, you have a general equation of showing it, because steady state creep is very important when it comes to applying, when it comes to application purposes. I'll tell you why in the subsequent note also, which I'll discuss. But it will have a general form like this: sigma raised to m dash into a into exponential minus qc by rt. So dependence on stress as well as temperature of the strain rate, steady state strain rate. I hope you have seen the creep curve well enough and understand how it is. Even with your eyes closed, you should be able to make the creep curve. Otherwise, you will not know what I mean by the steady state creep. So anyway, steady state creep is the portion of the creep curve where you have a constant strain rate, and it is of a usually constant value, and it is low value. The tertiary one, it will suddenly increase. And also there are certain microstructural features, it can differ, but generally the microstructural changes which occur in stage 1 and stage 2 are um, like in stage 1, sir has discussed this in detail. So in stage 1 you have dislocation, multiplication taking place, work hardening taking place, cell structures form, they become more denser, so their size reduces, dislocation density increases, that is causing the hardening. But after a point, you have also diffusion mechanisms operating, so dislocations are able to mm, by diffusion move like circumvent or surpass the obstacles. So that leads to reduction in work hardening. Recovery is taking place, causing reduction in dislocation density. So recovering is also due to diffusion. That also lead to a reduction in work hardening. So in stage 2, you have a balance of work hardening due to multiplication and tangling of dislocations, getting balanced by recovery and dislocations moving past obstacles by diffusion processes. These two are kind of countering each other. So you have a steady state strain rate. After that, in third stage, a flaw forms, and that will lead to start of failure, so quick propagation of cracks. That is the in essence in very short. Of course, there is more to it. You can look up in the slides for it. So next we'll look at stress rupture test, but let's take a short break, maybe 10-minute break, and then we'll come to stress rupture test and discussion of the some of the questions pertaining to week 8 of assignment 2023. Some portion of creep will not get finished in this session, like the end part. Till cobalt creep I'll cover. After that, there is some portion, so that I'll cover in the next session. I'll try to cover that and also finish week 9. If I'll just try my best to finish week 9 also in the next session, so that we are back on track. Right now we are a bit delayed. We are so let us do that after a 10-minute break. In the meantime, I'll just open the assignment questions for some of you to just take a look later on when you are seeing the recordings. Mhm. Let's continue. First, let's look a little bit more at creep. Just a minute. Mm. So till now we looked at creep test, where you have a minimum creep rate, also called steady strain creep rate, and I have not shown the diagrams of how the strain versus time and strain rate versus time curves look, but there will be a minimum creep rate which we call the stage 2 or steady state creep rate. Hmm. And that is one way of measuring creep. But there is also another kind of test called the stress rupture test. So in creep test, you are more concerned with what is the minimum creep rate you get, or how much time it takes to reach a particular strain and for a particular stress and temperature. But in stress rupture test, you want to see the load bearing capacity of the material. Yeah, you are more concerned with how much load can a material bear before it fails. So you look at time to rupture and the stress which was applied for different temperatures. And when we make these plots by studying the slope of the curves for different temperature, you can uh, get some information related to the mechanism that is operating, and if there is a change in mechanism, uh, that will be associated with a change in the slope of the curves also. So what are some creep mechanisms? One is the usual dislocation creep, sorry, dislocation glide. This is similar to what happens even in quasi-static loading, that is tension test, where you have dislocation glide, but there you have very minimum thermal activation, very low thermal activation. It's more stress based activation. But here thermal activation also becomes important because stresses are lower as well as temperatures are higher. So because of that, this mm, So because of that, thermal activation will also have a effect, and we give it by this equation, the creep, the strain rate due to dislocation glide. Here U naught is the for total activation energy for the glide to occur. That is one atomic bond switching to occur, and tau is the shear stress applied. Tau, and you have some dependence on the temperature. So this temperature dependence is associated with the thermal activation actually. Then you can also have other mechanisms involved in creep, which are more diffusion based. So one is Nabarro Herring creep, where you have vacancy diffusion through the grains being the dominating factor, leading to your straining of the material. So due to tensile stresses which have been applied while loading, there will be a flux of vacancies from one region to another within the grains, and that will cause strain. This can be given by these equations, where n is the number of vacancies, equilibrium number of vacancies or vacancy concentration in the tensile and compressive regions. It will be different in both these regions because the uh, local volume or the atomic volume will change uh, in case of tension and compression. In compression, you have atoms being pushed towards each other. In tension, they are farther away from each other. That leads to a change in the local volume or atomic volume, you can call it, and that leads to a change in the equilibrium number of vacancies that you will have in that condition. Because of this, there is a concentration gradient and you will have a flux of vacancies. This flux of vacancies from one region to another will lead to parallel uh, change in the number of atoms in those regions, and that basically translates to some straining of the specimen or a change in the shape of the grains. So this is the equation for Nabarro-Herring creep strain rate. There will be dependency on stress, but a strong dependency on the grain size also, because we can see diffusion occurs through the grains, because due to change in grain shape that you get the strains. Similarly, this is more dominant at high temperatures only, where dislocation glide related contributions are very low and at very low stresses. So similar to this, you can also have another mechanism where the uh, diffusion is mainly through the grain boundaries, along the grain boundaries, and not as much in the you can call it the meat or the flesh of the grains or matrix or the interior of the grains. So in that case, you call it cobalt creep. This happens at lower temperatures, more dominant at lower temperatures, like still above zero point 0.5 tm, but lower compared to that of NH creep, because the activation energy for diffusion, vacancy diffusion along grain boundaries is much lower than that in the interior of the grain. So comparatively lower temperatures will lead to dominance of cobalt creep due to grain boundary diffusion, diffusion along grain boundary, and it will also have a similar equation, just that you will have a change in this activation energy because the mechanism has changed. There will be some term related to grain boundary volume or thickness of grain boundary. and then you will have a cubic dependence on the grain size. So grain size becomes much more, it will be more sensitive to grain size compared to NH creep. Hmm. So these were NH and cobalt creep. Also, when these diffusional flow based deformation is occurring, you have a change in the grain shape, as I told. So there's a direct effect of change in grain diffusion to change in grain shape, and that is connected to staining of the sample, change in the uh, total dimensions of the specimen. But to accommodate this change in grain shape, you need to you need to along with this change in grain shape, you need to maintain the compatibility at the grain boundaries. There should not be any void forming between the grains, as that will lead to flaw creation, and quickly stress can concentrate and lead to failure. So in order to um, accommodate this compatibility at grain boundary, you will have some grain sliding taking place. And I think there have been studies which have used certain markers and certain techniques to show that grain sliding does take place when these creep mechanisms are occurring. And these are some very elegant studies. I have seen some results. You may also check maybe if curious. So sliding of grain boundaries is happening parallelly along with the diffusion of vacancies, and together they are ensuring that you have both creep taking place, as well as there is no uh, critical flaw creation which can lead to failure. So that was all about creep that we'll discuss in this session. Some portion is left, which, as I said, we'll discuss in the next one. Let's look at assignments now. Hmm. Uh, Almost majority of, there are less of numerical, and because this is more on these are more of phenomenological models, as we see for thermal glide, uh, cobalt creep, Navarro Heron creep. It's based on certain mechanisms that we have uh, hypothesized that they occur, or that we have seen experimentally also in some ways. And then based on that, we are building up the maths to get some relations. And similar to constitutive relations, but this is even more phenomenological. And then you are using those equations, and then you are validating those equations by seeing experimentally whether these are the trends that you are actually getting, or these are the relations between parameters that you are actually getting in the experiments. So let's look at the questions. Hmm. Statement 1: onset of tertiary creep is greatly reduced in case of a constant load test as compared to a constant stress test. Hmm. Onset of tertiary creep is going to be higher for a constant load test, right? You have seen the curves which were shown in professor slides, that this is your strain, this is your temperature, time. Constant stress test will be something like this. Constant load test will lead to much earlier tertiary creep initiation. So this will be something like this. This is because in the constant load test, as your specimen cross section is reducing, the applied load is not changing. So your stress, true stress, is in essence increasing as the strain is increasing. That will lead to more accelerated failure in the tertiary stage. While in case of true stress one, you can go like constant stress, you can go to much higher strain values without having the increase in the true stress, because true stress is so true stress is constant. You can get much higher. Um I am not actually. This is not factually correct. You cannot have zero strain rate in between. You will have some. It will be something like this. Some constant strain rate, then tertiary creep, and for steady state it will go on for higher time compared to for the uh, for true state it will go on for a higher time compared to the constant load one. Yeah. So this is the load, constant true stress. The first question is false. Statement 2, during primary creep, the creep resistance decreases by virtue of its own deformation. No, it's by virtue of its own deformation. Let's try to understand that, what that could mean. I'm not sure about this. And during primary creep, there is creep resistance increasing in a way, in a sense, because strain rate is decreasing. But that is because work hardening is taking place. So it should actually be false as per my understanding, because if work hardening is increasing, the creep resistance is actually increasing during primary creep. With increasing temperature, the duration of steady state creep becomes longer. Steady state creep is because of the uh, is because you have balance of recovery as well as work hardening. But the steady state creep strain range will increase with increasing temperature, that is for sure. But the strain rate will also decrease. Sorry, strain rate, the steady state creep strain rate will also increase with increasing temperature. So both the rate changes increases as well as the strain range changes. About duration, it will be difficult to tell. I think it will be lower because so I think the steady state creep duration, that is time of this steady state stage, will be lower because to get to the same strain value you will require less time because your creep rate has essentially increased. So higher creep rate corresponds to lower time to achieve a particular strain. So this will be false. This you can also understand from application point of view, that if your temperature is high, then your component life decreases because it will creep much faster. So in a way, the duration of steady state creep, which is occurring in your component during its life, has reduced at higher temperature. The change in mode from fracture or fracture from intergranular to intragranular can change the slope of the stress rupture curve, but formation of new recrystallized grains has no effect on the slope. This, no, any change in your microstructure or the properties of the microstructure will lead to a change in your mechanism, and so that will change the slope. So it could be that it's going to get fracture is changing from intergranular to intragranular. So that will have some effect. Maybe it will rupture faster for one of them, but new recrystallized grains will also have some effect. Maybe that can increase or reduce the tendency to fracture, but this is false. All are false. All are false, right? Hmm. But here it says the second statement is true, which is, I didn't understand the second one well. I tried to think more on it. It doesn't seem, I don't know why it should be true or what this will mean. Creep resistance decrease. I look at it. Let me just mark it. Let's go to the next question. When load is suddenly applied in the beginning of a creep test, material undergoes an instantaneous strain. If the applied stress is less than the yield strength of the material, which of following are the different components of the instantaneous strain? There is instantaneous strain. Applied stress is less than the yield stress. And what are the components of the instantaneous strain? There will be recoverable elastic strain. I don't think there is any time dependent elastic strain. There is nothing of that sort in actually. Elastic strain is always time independent only. Non-recoverable plastic strain. Mm, but it won't be there because recoverable plastic strain, I don't think there's anything which exists. Can C exist? C be true? Non-recoverable plastic strain, even though it is less than the yield stress, there can be some plastic strain. Like locally in some grains, you might have plastic deformation, which always occurs. It's never a sudden transition from elastic to plastic. Locally in some grains, you might have plasticity before yield stress, so this is possible. Microplasticity is the term used for that. Maybe it is A and C. It says B is also correct. Time dependent elastic strain. Maybe it's just that you are loading in the machine. Is a machine related characteristic that when you are loading it, it takes some time for the load to get applied or the strain to get measured. Very likely the strain measurement takes some time, so that can be called time dependent elastic strain. I'm not sure, but this is also a bit gray area, ambiguous. Okay, let's see the next question. I'll look at these again after the class and try to understand. Then I'll let you know if there is any change I feel in the answer key. Grain boundary sliding can be promoted by increasing strain rate, decreasing temperature. I think the answer grain boundary sliding will be easier at higher temperature because higher temperature the grain boundary strength is lower, right? We had seen equicohesive temperature, what it is. So at higher temperature, grain boundary strength is lower, so it should help. And grain boundary sliding essentially is time dependent process, highly time dependent, I feel, because you have grains sliding against each other, which will, and it has to do it in a complex fashion so that all the compatibility is ensured at the end of it between the grain. So it will be a time dependent process. So reduced strain rate will promote grain boundary sliding. I guess answer should be none of them. Let's see what what's the correct answer. Okay, yeah. Else this also might have become a ambiguous question. Okay. In Orovan creep model, where both dislocation glide and climb take place due to the combined effect of stress and temperature, which one of these accommodate more amount of strain? Actually, I have not discussed it in my summarization yet. The correct answer is glide, I know, which is the rate controlling step, atomic diffusion. But I'll cover it again in the next one. So for now, I'll just mark it so that we can next time look at it because the Orowan creep has not been covered in my summarization yet. Let's go to next cobalt creep. Question 6. In cobalt creep rate depends on the grain size as we have seen. It's grain boundary based creep and the dependence was because the grain it's somewhat related to the fraction of grain boundaries in your material and that was more sensitive to the grain size compared to the grain size compared to NH creep where you have the processes taking place within the grain interior of the grain. So in this you have a cubic dependence and it will be 1 by d cube. Larger the grains, smaller the creep rate because less grain boundary area is there and diffusion will have to take longer paths. So it's d cube. In NH we have d square. To understand that you have to look at the derivation. what all factors are coming in. The conditions at which NH and cobalt creep is favorable are both require somewhat high stresses, lower, sorry, lower stress, high temperatures and lower stresses because they're competing with dislocation glide. If their stresses are high, dislocation glide will definitely get favored. And at high temperatures only, these diffusion based mechanisms will be able to dominate. So high, low stresses and high temperature. Actually, even okay. And also, since you have options related to grain size, finer grain size, easier diffusive processes, Mm, more of diffusive processes. Creep involving stress directed atomic diffusion as the dominant creep strain mechanism is of the dominant creep strain mechanism. Stress directed atomic diffusion. Hmm. Dislocation glide, it's not Nabarro herring, we know. Not stress. Nabarro herring is also stress dependent, but it has lower contribution of stresses. You can have dislocation creep, power law creep. Actually, we have not looked at in detail. Mm. Power law creep is more involving dislocation climb followed by glide. I think it's dislocation glide, which is stress directed, but their diffusion plays a very small role. Mm. Let's look at this later on when we have looked at power law creep and all. In the next session, we can look at this. Actually, I have seen the answer, but fine. We'll look at this in the next one. We have not yet covered over Orvan based creep, and power law creep is also the same thing, but there's this Orowan creep model and power law model. Then match the following creep mechanisms with the conditions favored for them. Power law creep, global creep, Nabarro herring. Nabarro herring will be that is, Cobalt will be grain boundary. Power law will be at high stresses. We'll look at it in the next one. So A3, B2, C1. Power law creep is more of stress based because it involves dislocation and glide. Which of the following statement is correct? The engineering design criteria for materials at high temperature applications involves minimum creep rate. Yeah, true. Minimum creep rate tells a lot about the life of a component. So it goes into the design criteria. Steady state creep involves balance between work hardening and recovery. True. Region of creep curve in the tertiary stage involves decreasing creep rate. Not true. Increasing creep rate. False. Tertiary is accelerated creep. Grain boundary sliding in high temperature deformation of superplastic materials occurs at high strain rate as compared to in diffusional creep. In high temperature deformation occurs at high strain rate as compared to in diffusional creep. I think so. It might be true in superplastic materials. Grain boundary sliding also takes place even if you have quasi-static kind of loading, that is high strain rate. I think it should be true. Creep is a time dependent deformation. Maybe this will be covered in next session. Creep is a time dependent deformation phenomena only at high homologous temperature. So sir had clarified initially that it is more dominant usually at high temperatures only, but even at low temperatures. High and low are very subjective. You cannot just say uh, so. One thing is high and low are subjective, but here we have high homologous temperatures. That means high value of temperature with respect to melting point. But even at low, it does occur. So those are kind of exceptions, but I'll say that this is a false statement. It can occur. So the only thing makes the difference. You can't say only. So the true statement is, which is incorrect, false. Oh, the third one is incorrect. So the fifth one is correct, it's saying. Okay, maybe it occurs at high homologous temperature only. But some materials like titanium are known to show room temperature creep, which is low homologous temperature. So in certain materials, just exceptionally it happens. You can say 99% it does not happen. So even true might be fine. Just write this as true. Because diffusive processes only occur at high homologous temperature. That way you can explain this. Question 11. The conditions for material to exhibit superplastic behavior are superplastic behavior. Hmm. Conditions to exhibit superplastic behavior are fine grain size is known, grain boundary sliding occurs much more in fine grain size. So grain boundary sliding is one mechanism which dominates, which causes superplastic behavior. That is very high strains are possible, very high plasticity. High temperature also will help in that for having very high plasticity. Plastic deformation is very easy. And low strain rate, well, strain rate sensitivity. Oh, this is a tricky one. Strain rate sensitivity. So, seeing it just mechanistically, if you are if you do not want it to neck, then you want that if a portion of your sample has become thinner, it should have very high strain. That means the because in that portion the strain rate has increased. So the strength also should increase significantly in that portion so that necking does not happen. So strain rate sensitivity should be high if you want super plastic so that your even in your thinner, less cross-section regions, you do not have necking taking place easily. The strength of that region is high. So high strain rate sensitivity. Let's look at the answer. Oh, yeah, this was a good question. Last question. You have this is about LM parameter, which we have not discussed yet. So you have two materials, their LM parameters. Which material would be stronger if Ca less than Cb and the curves of sigma versus P coincide? LM parameter is related to the life of the material. Let's look at it in the next one. Temperature into I also can't recall. Let's look at it in the next session when we cover this portion. Okay, so with this, we have finished some portion of week 8. The rest I'll cover along with week 9 in the next session, and we'll also look at the questions for that. If you have, as I have said, if you have doubts, post in the discussion forum. I'll take it up and continue learning. Study well. About 8 out of 12 weeks are done, so that is about 66% of your 65% of your course is complete. So I hope you all are enjoying it. You are able to keep up with the contents and solving the assignments. So all the best to you all. We'll finish now. Thank you.